Hello friends, welcome to Mechanical Engineering online classes.
Simplex method is a technique or an algorithm that helps us get the optimal solution for any linear programming problem. If we want to compare the simplex method with the graphical method, we know that the graphical method can be applied only for a two-variable problem, whereas simplex can be applied to any number of variables of an LPP. And not just that, while solving an LPP using graphical method, we find the solution space, and substituting each vertex into the objective function, we have to find the optimal function. Whereas the simplex method provides an algorithm which consists in moving from one vertex of the feasible solution region to another vertex in such a way that the value of the objective function at the succeeding vertex is better than the preceding vertex. It might be a maximized type of problem or a minimized type of problem. In every iteration, our Z gets better. So let us learn simplex method using an example. So let us consider the following problem. The objective is to maximize. The objective function is Z, which is 2x1 plus 5x2. This should be maximized, which is subjected to several constraints. The first being x1 plus 4x2 is less than or equal to 24. 3x1 plus x2 is less than or equal to 21 is the second constraint. x1 plus x2 should be less than or equal to 9 is the third constraint. And x1 and x2 both should be greater than or equal to 0. This all the variables being greater than or equal to 0 is the non-negativity restriction. Now let us write the given LPP in standard form. So this is the standard form for the given problem for all xi and si greater than or equal to 0. So in standard form, every inequality is converted to an equation, all RHS being positive for the constraints, and all the decision variables must be in terms of all decision variables and introduced variables, our S1, S2, S3, these are the slack variables. So every variable that we are introducing should also follow the non-negativity restriction, means all of them must have a minimum of 0 value, they cannot be negative. And every expression including Z should be expressed in terms of all the variables. That is a standard form. So if you do not know how to write a standard form or the rules of the standard form, you can check our previous video. The link will be provided in the description box. So starting from formulation of an LPP to writing it in standard form, and even graphical methods are all already there in the operations research playlist or optimization technique playlist. The links are given in the description, you may follow them. Now this entire thing is a standard form, LPP written in standard form. So from the given LPP, it is clear to us that the number of equations is 3 and the number of variables is 5. So m is less than n. So we have to find a solution using the basic solution concept. The extra number of variables, which is n minus m, must be equated to 0, and we have to find the remaining m variables. So simplex iteration always starts from origin, because x1 and x2, their least value is 0. They can be 0 or more from this non-negativity restriction. So the first cycle or the first iteration starts from origin. So x1 and x2 are set to 0. So first the decision variables are set to 0. So x1 and x2 are set to 0. So this x1 and x2 are the non-basic variables here. So in short, from now on I'll be calling it as NBV, non-basic variables. And substituting x1 and x2 as 0, we can find the corresponding S1, S2 and S3 from these three equations. So S1 and S2, S3 will be basic variables. In short, I'll call it as BV. So if you're not understanding what a basic solution is or what non-basic variables or basic variables are, so you can find the link in the description. It is already clearly explained. Now for this combination of values or this set of values, so keeping x1 and x2 as 0, we can find s1, s2 and s3. So when x1 becomes 0, x2 becomes 0, s1 will come out to be 24, s2 will come out to be 21. Similarly, s3 will be 9. And the z value, corresponding z value for a combination of x1 equal to 0, x2 equal to 0 and s1 as 24, s2 as 21 and s3 as 9, corresponding z value will be 0. Substituting this x1, x2, s1, s2, s3 in this z, the value of z will be 0. So that is a basic feasible solution. It is a basic solution and also feasible solution. So this is our first iteration, first cycle. So this will be our, this solution can be called as initial basic feasible solution. Initial basic feasible solution, in short IBFS. So let us draw simplex table for the initial basic feasible solution. IBFS, we got z as 0. So here the table will have all the constraints shown. BV is a basic variable, we know that. CB is the coefficient of basic variable in objective function and CJ is the coefficient of variable in objective function. So let us see what it means. CB is a coefficient of basic variable in objective function. So in initial basic feasible solution, the basic variables are S1 from first constraint, S2 from second constraint and S3 from the third constraint. And their coefficients in objective function are 0, 0 and 0. So CB for three basic variables is 0. And CJ is a coefficient of variable in objective function. So for x1, the coefficient of x1 in objective function is 2. So let us write 2 here. 2 is for x1. For x2 it is 5. For S1, S2, S3 it is 0, 0 and 0 respectively. So we can read the objective function from the table. It is 2 into x1 plus 5 into x2 plus 0 into s1 plus 0 into s2 plus 0 into s3 is the objective function. Now let us write the coefficients of all these variables that come for every constraint. The first constraint from where we get the value of s1, let us write these coefficients in this particular table. So it is 1 into x1 plus 4 into x2 plus 1 into s1 plus 0 into s2 plus 0 into s3 is equal to 24, where b is 24, which is our first constraint. So we have written the first constraint here. 1 into x1 plus 4 into x2 plus 1 s1 plus 0 s2 plus 0 s3 is equal to b. b is nothing but the resource, which is 24. Similarly, let us take down the second constraint. Second constraint is from where we get the value of s2. If s2 is written here, we must be writing the coefficients of variables from that constraint where from we get the value of s2. We cannot write just any constraint anywhere. If you want to write the third constraint variables here, you have to write this as s3. And you can put the second constraint values here and make it s2. That way we can exchange. Otherwise, if at all we are writing s2 here, then s2 is coming from second constraint. Those variables only must be added here. Otherwise, no. So keeping the variables of second constraint into this, it is 3, 1, 0, 1, 0, 21. So 3 into x1 plus 1 into x2 plus 0 into s1 plus 0 into 1 into s2 plus 0 into s3 is equal to b, is the second constraint. In a similar fashion, we shall write the third equation here. It is 1 for x1, 1 for x2, 0 for s1, 0 for s1, 0 for S2 and 1 for S3. Under resource we have 9. Now the entire LPP is written in tabular form. Here the basic variables are clearly mentioned. Their contribution is also mentioned in Z. Then all the variables have the objective function is mentioned, the constraints, everything is mentioned. So let us find Zj, which is the contribution that is lost per unit of variable. The formula is this: summation of CB, the summation of product of CB and Aij. Aij is these values, these 1, 4, 0. They are called as the technological constants, right? So under x1 variable, it will be 0 into 1 plus 0 into 3 plus 0 into 1, which will be 0. Similarly, under x2, we have 0 into 4 plus 0 into 1 plus 0 into 1, which is again 0. Similarly, no matter what the technological constants are, because they are multiplied by CB, which are all zeros, we have Z as 0, 0, 0 under every variable. And even under B also, how do we find the final Z value? It is 0 into 24 plus 0 into 21 plus 0 into 9. That is nothing but 0. So this 0 is the initial basic feasible solution. That is what was obtained here, right? We got S1 as 24, S2 as 21, S3 as 9, but because the coefficient of S1, S2, S3 are all zeros, and whichever variables had a good coefficient, they were set to 0. So ultimately Z became 0. This is our initial basic feasible solution, right? Now the same can be read from the table here. How do we read it? The value of S1 is 24. The value of S2 is 21. The value of S3 is 9. These are the basic variables. All other variables are 0. Did we get the same here? 24, 21, 9. And similarly, the value of Z came out to be 0. This is our initial basic feasible solution. So straight away from the table we can read the objective function, the constraints, and the corresponding values of the basic variables. Now let us find the net evaluation row as Cj minus Zj. So this is called as net evaluation row or index row. Cj is nothing but, this is 2, this is 0. Cj minus Zj means C1 minus Z1 is 2 minus 0, which is 2. Similarly, under the second row it is 5 minus 0 means 5. Here it is 0 minus 0 is 0. 0 minus 0 is 0. 0 minus 0 is 0. So let us clearly understand what this NER, the index row or the net evaluation row, shows. As the name suggests, it is actually the net profit in Z for each unit of the respective column variable that is introduced into the solution. What does that mean? Here our objective is to maximize. When Z has to be maximized, if we clearly look into the variable coefficients, say for example in the given question, x1 might be the number of units that the company should sell of product A, say. x2 is the number of units that the company should be selling of product B. And if in case for 1 unit of product A, the profit is say 2 rupees or $2, then for selling x1, the profit is 2x1. So similarly, in case the product B on sale, if the profit is say 5 units, then for 1 unit of product B, the profit is 5. So for x2 number of product B, the profit will be 5x2. And S1, S2, S3 are actually those slack variables which we have introduced so as to write it in the standard form. Why should it be written in standard form? You can clearly see it here. We are completing the matrix. We cannot leave empty spaces into the matrix. right? Why is it written in the matrix form? Because we know that we are going to solve, whether it is the optimization techniques or the operations research, we are trying to bring out a solution to a real life problem. And when we have to address a real life problem, the number of variables and the number of constraints keep changing, and they may be in hundreds or thousands of numbers. The number of variables might be some thousands, the constraints might be hundreds. So we cannot manually solve all of those. We are just learning how the algorithm works, so that we can later program it. So in the program, we will give the size of the number of variables or the number of equations, and then all these values, what we are seeing here, the technological constant, the constraints, they are all fed into the computer. And when we are feeding them as elements of a matrix, we cannot feed incomplete matrix. If at all I am saying it is a 4x4 matrix, it should have all 16 entities. If at all it is a 3x4 matrix, it should have all 12 elements. I cannot feed in only 3 or 4. So this is the reason why in standard form we write every expression in terms of every variable, whether it is already there or whether it is a slack or surplus or an artificial variable, doesn't matter. You have to show all the variables in every expression. The level or the contribution of that variable will be shown in every expression. So this is a necessity. Now if we check into our index row Cj minus Zj, Zj is a contribution that is lost per unit of a variable. Now what is Cj? If at all I want to maximize my Z, I want a maximum profit out of the 2x1 plus 5x2 plus 0x1 plus 0x2 plus 0x3. I can maximize Z only when I give some value to x2, because x2 is having a higher positive coefficient compared to 2 and 5. It is better I give some value to 5. The moment for some value to x2, the moment I give a value to x2, the Z will become maximum. So that is what can be seen in this table. This is the profit. This 2, this 5, this 0, this 0 and this 0. These are the profits when we introduce those variables into the solution. So if at all I am picking this particular 2, if at all I am taking x1 into the basic variable set, then one unit of x1 is giving me 2 profit. So x1 number of units will give me 2 x1 profit. So here the next one is 5x2. So if one particular product B, 1 unit of product B can give me 5 units of profit. So x2 number of product B will give me 5x2. So it is 5 times multiplied. So of 2 and 5, whatever is a maximum, let us pick that. And one more thing, we cannot sail in 2 boats. We have 3 basic variables, because of which we have only 3 constraints, so we can have only 3 basic variables. So from S1, S2, S3 we will have to kick one out, so that I can kick in x2 into the basic variable solution. Let us see how. So before that, remember that Cj minus Zj, the net evaluation row or the index row, represents the net profit in Z for each unit of respective column variable. These things, when that variable is introduced into the basic solution. So in management terms, they are also called as shadow prices or accounting values or imputed values of resources. These are the other names. So if you see the index ratio under S1, S2, S3, the net evaluation row shows us 0 values. 0 values because the contribution of S1, S2, S3 in maximizing Z or minimizing Z, it is 0. The slack variables are having 0 coefficient in Z. So no matter what value S1, S2, S3 can take, they have taken very high values, 24, 21, 9, but it really doesn't matter, because ultimately their contribution in getting the best Z is 0. So that is the reason we got a 0, 0 and 0 here. So we will introduce x2 into our basic solution. So x2 must be the entering variable, because because introducing x2 will give us higher profits. So this is the x2 column. So the entering variable column is called as key column or pivot column, x2 column, because x2 will be introduced, because introducing x2 is giving us high profits. Because it is a max type of problem, we have to pick that variable as entering variable which is having most positive value. It is most positive. In case of a minimized type of problem, we must be picking the most negative. So when NAR shows the most negative, that variable must be considered to be an entering variable for min type of problem. Here we need maximum profit, so we need most positive value only. So x2 column is called as the pivot column or key column. Now if x2 is the entering variable, at a time we can solve for only 3 variables. So if at all x2 is made to be a basic variable, one of the S1, S2, S3 must be out of the basic variable. So one of them must be made a non-basic variable. In this particular first table, S1, S2, S3 are the basic variables. So x1, x2 are non-basic variables. So if x2 must be made a basic variable, one of these 3, S1, S2, S3 must be made a non-basic variable. But how do we decide which variable should be made non-basic variable? For that we have to find the replacement ratio, RR, replacement ratio or minimum ratio. This is found as the ratio of BI divided by pivot column ith coefficient. So the minimum ratio or the replacement ratio must be found for all the 3 basic variables, for S1, S2 and S3. How do we find that? We have to find BI. So for S1 we must be finding B1, which is 24, divided by pivot column's ith coefficient. Pivot column is the x2 column. So pivot column ith coefficient is 4. So 24 by 4. This is 6. So similarly for S2, it is B2, which is 21, divided by pivot column ith coefficient. Ith coefficient is this one, which is 1. So it is 21. So in the similar fashion for S3 it is 9 divided by this 1, which is equal to 9. As the name suggests, minimum ratio means whichever ratio is minimum, that particular corresponding variable. Here it is S1. 6 is the minimum of 6, 21 and 9. So S1 must be the leaving variable. So the basic variable set will now comprise x2, s2 and s3. So while picking the minimum ratio, we have to see the minimum non-negative value. So it can be 0 also. So even if we have a 0 as minimum ratio, that will be considered as the minimum. But in case say in place of 6, 21 and 9, if we are getting all zeros or zeros and infinity, then solution in that case is unbounded. So now we know that S1 is the leaving variable. S1 is leaving variable and x2 is the entering variable. So the leaving variable row is called as pivot row. Pivot row or key row. Similarly, the entering variable column is called as key column or pivot column. And the intersection between the pivot row and the pivot column, that element is called as pivot element or key element. Here the key element is 4. What we are seeing in this table 1 is what we have got under our IBFS. the value of S1, S2, S3 can be straight away read from this table. S1 is nothing but this. S1 is nothing but 24. S2 is nothing but 21. S3 is nothing but 9. And the corresponding value of Z is 0. So that is what is our IBFS, right? S1, S2, S3 and Z. So to improve Z, we are modifying our basic variable set. So in place of S1, S2 and S3, we will have X2, S2 and S3. So we shall rewrite this table for the values of X2, S2 and S3. So let us rewrite the table. This CB, BB, basic variable, X1, X2, S1, S2, S3 and BD. Coefficients of X1, X2, S1, S2, S3 in Z are 2, 5, 0, 0 and 0 respectively. Now under basic variable, what do we have under basic variable? In place of S1, X2 should come. So this is X2. Then S2 and S3 are the other basic variables. So let us write S2 and S3 here. Coefficients of basic variables in Z are, coefficient of X2 in Z is 5, for S2 it is 0 and for S3 it is 0. So this will be 5, 0 and 0. Now let us see what to write in place of the first constraint. The first constraint in first table is straight away the given constraint, which is x1 plus 4x2 plus s1 is equal to 24. So the simplex table is written in such a way that straight away from the table we can read the values of the basic variables, like s1 is equal to 24. Why is x1 equal to 24? Because if at all we want to write this first row as an equation, we can write it as 1 into x1, this is 1 into x1 plus 4 into x2 plus 1 into s1 plus 0 into s2 plus 0 into s3 is equal to 24. Because x1 and x2 are non-basic variables, these are zeros, and because s2 and s3 are having 0 coefficients, this also becomes, this entire term becomes 0. So straight away we are getting s1 is equal to 24. 1 into s1 is equal to 24. So it is because of this pattern or the style of representing the equation, we are straight away able to say that s1 is equal to 24. But now when we want to rewrite, we want to write the modified simplex matrix, we must write the constraint here in such a way that we can read the value of x2 as x2 is equal to something here, s2 is equal to some value here, s3 is equal to some value in here, and therefore z is equal to something. And so for that we have to apply some row operations on the given matrix. We have to apply the row operations in such a way that, like how s1 to s1 is 1 and s1 to s2 s3 are zeros, similarly s2 to s2 is 1 and s2 to s1 or s3 is 0, and similarly s3 to s3 is 1 here and s3 to s1 or s2 is 0 here. That means the part of matrix that belongs to basic variable set is an identity matrix. Because it is an identity matrix, we are straight away able to read the value of basic variable from the given table. So here also when we are writing a modified table, we have to see that the basic variable set should become an identity matrix. What does that mean? Means x2 to x2 should be 1, s2 to s2 should be 1, s3 to s3 should be 1, and x2 to s2 or s3 should be zeros, s2 to x2 or s3 must be 0, and s3 to x2 or s2 must be 0. So this becomes an identity matrix. So in order to make this identity matrix, or in order to change these technological constants into ones and zeros from the original one, we have to apply the Gauss-Jordan method. So using this method, we will be converting our previous constraints to a new constraint without changing the meaning. So for your comfort, I will write it down as a formula based on the previous row to write the corresponding new row. I will write it in the form of a formula that is been obtained from the Gauss-Jordan method. So first let us start writing the entering variable row. Entering variable row is, what is entering variable? It is EV, which is x2, the pivot column. Pivot column gives us the entering variable, which is x2. So x2 should be written as, x2 row should be written as, which is the entering variable row, is equal to leaving variable row divided by pivot element. What is a leaving variable row? What has left? It is S1. It is S1 that has left. Leaving variable is LV. S1 is left. So S1 elements are 1, 4, 1, 0, 0 and 24. So x2 row is equal to S1 row divided by pivot element is 4. So therefore x2 row will be, the new x2 row will be equal to, what is S1 row? That is 1, 4, 1, 0, 0, 24. This all elements must be divided by 4. So we can write this as 1 by 4, 1, 1 by 4, 0, 0 and 6. Now these are the elements that we have to write for x2. So this is 1 by 4, this is already 1, this is 1 by 4, 0, 0, 6. So x2 row is written. Now we have to write the new S2 and S3 rows also. We have already seen how to write entering variable row. Now we will see how to write the other rows. For other rows, we will find the new row as the current row minus its pivot column coefficient multiplied by the new pivot row. Now for example, if we want to write the new S2 row. S2 row, old S2 row is here, 3, 1, 0, 1, 0, 2, 1, 21. That is the old one. So if you want to write the new one, then new S2 will be equal to the old S2 row minus its pivot column coefficient. Let us see what that is. Its pivot column coefficient is this 1. This 1 is its pivot column coefficient. Because pivot column is this 4, 1, 1. This is the pivot column. So what is the element that is corresponding to S2 row? It is this 1. So here it is just 1. Pivot column, its pivot column coefficient is 1 multiplied by the new pivot row. New pivot row is nothing but our entering variable row. This is it, the x2 row. So that is x2 row. So this is how we will find the new row when it is not an entering variable row. So let us find what old S2 is. Old S2 is nothing but 3, 1, 0, 1, 0, 21. This is equal to 3, 1, 0, 1, 0, 21. Minus 1 into x2 row is directly the x2 row. What is x2 row? It is this 1 by 4, 1, 1 by 4, 0, 0, 6. Or we can simply subtract like this. Then we have 3 minus 1 by 4 is 11 by 4. 1 minus 1 is 0. 0 minus 1 by 4 is minus 1 by 4. 1 minus 0 is 1. 0 minus 0 is 0. 21 minus 6 is 15. So we are subtracting from the corresponding element. So now we have the S2 new row. Let us write this in the simplex table. This is 11 by 4, this is 0, this is minus 1 by 4, 1, 0 and 15. So in the similar fashion we have to find the new S3 row also. So new S3 row is equal to old S3 row minus its pivot column coefficient. S3's pivot column coefficient, corresponding pivot column coefficient is 1. So this is 1. So let us write the old S3. Old S3 is 1 1 0 0 1 9 minus x2 row is 1 by 4 1 1 by 4 0 0 and 6. So 1 minus 1 by 4 is 3 by 4, 1 minus 1 is 0, this is minus 1 by 4, this 0 minus 0 is 0, 1 minus 0 is 1, 9 minus 6 is 3. So this is our new S3. Let us write this in here. This is 3 by 4, 0, minus 1 by 4, 0, 1 and 3. So straight away from this table we can read the values of x2, s2 and s3. x2 value is 6, s2 value is 15, s3 value is 3. So let us find zj. Zj will be equal to 5 into 1 by 4 plus 0 into 11 by 4 plus 0 into 3 by 4. That is 5 by 4. So similarly here it is 5, here it is 5 by 4, here it is 0 and 0. And value of z, total z based on what values we have for x2, s2 and s3 in the original objective function is 5 into 6 plus 0 into 15 plus 0 into 3, that is 30. So for the given values of x1, x2, s1, s2, s3, x1, s1 are zeros, x2 is 6, s2 is 15, s3 is 3. So when we substitute the obtained x1, x2, s1, s2, s3 in this given question, in this z, then we will get it as 30. So we are getting that, we can see that here. So if we compare our present z to the previous z, our objective is to maximize z. So z has become better. So from 0 it came to 30. So z is getting better in every iteration in this particular method of simplex. But we do not know whether this is also the best solution or not. So for that we have to again find the index row, net evaluation row, like how we have already evaluated for the first table, NER. So this is 2 minus 5 by 4, that will be 3 by 4. This is 5 minus 5, 0. This is 0 minus 5 by 4 is minus 5 by 4. 0 minus 0 is 0. 0 minus 0 is 0. As we have already discussed what this NER is, it is a net profit in Z for each unit of the respective column variable that is introduced into solution. Now for example, if we check with the NER for x2, s2 and s3, it is 0, 0 and 0 because x2, s2, s3 are already, their contribution is already there. So for a basic variable means which is not set to 0. We are not setting the values of x2, s2 and s3 as zeros, right? We have chosen x2, s2 and s3 as a basic variable set. They are already contributing to the maximized z. So that's the reason our NER shows them as 0. Now if we pick s1, this is a minus, it is showing a negative, means if at all we are introducing s1 into the basic variable set, our z will diminish, the value of z will come down. That's the reason it is showing a negative value. The proof is already here. When s1 was there in the basic variable z, our z was 0 or whatever it is lesser than what it is now. So introducing s1 will only bring our z, which is 30, to lesser than 30. So that's the reason s1 should not be introduced, it is negative. Now to maximize NER, which is Cj minus Zj, should be positive. So x2, s2, s3 has got nothing to do. S1, it will only give us a loss. x1 we can introduce. x1 is among all the values in Cj minus Zj, the most positive value must be picked for a max type of problem, right? So the most positive is this one, and this corresponds to x1 variable. So now our entering variable is x1. Now x1 should enter into basic variable set. So there must be some variable that should leave so as to make place for x1. So for which we have to again find the replacement ratio or the minimum ratio RR as pi divided by pivot ith coefficient, just like how we have found here. So similarly we should be finding there. We already got the pivot column. Let us see which will be the pivot row. So here it is 6bi is the first b divided by its pivot ith coefficient, which is 1 by 4. 6 by 1 by 4 is nothing but 6 into 4, which is 24. So for this it is 15 divided by 11 by 4. That means it is 60 by 11. Here it is 3 divided by 3 by 4, which is nothing but 4. So this comes around 5.45. So in all these things, the most minimum non-negative is this. So this will be chosen as the pivot row. So what is the leaving variable? Leaving variable is S3 and the pivot element is 3 by 4. Now we have to go to write the next table, a modified simplex table in the same fashion using this formula. First we will be writing the entering variable row as leaving variable row divided by pivot element. Let us see that. Now what is our basic variable set? x2 is as it is. This is x2. Then s2 is also remaining. This is s2 and s3 is a leaving variable. In place of s3 comes x1. This one. So coefficient of x2 in z is 5. For s2 it is 0. For x1 it is 2. Now first let us write the entering variable row, that is x1 row. x1 row is equal to our old s3 row divided by pivot element. That means it is 3 by 4, 0, minus 1 by 4, 0, 1, 3. All these elements are divided by 3 by 4. So this will become 1, 0, minus 1 by 3, 0, 4 by 3, 4. So this will be the new x1 row. Let us write that here. 1, 0, minus 1 by 3, 0, 4 by 3, 4. And we also know the formula for other rows. We need new x2 row and new s2 row. So let us start with x2. New x2 row is equal to old x2 row minus its pivot column coefficient. We can find this pivot column coefficient in the previous table, this one. So it is this 1 by 4. 1 by 4 multiplied by the new pivot row. New pivot row means what we have just obtained, the x1 row. So here it is. Old x2 row is nothing but here 1 by 4, 1, 1 by 4, 0, 0, 6. That is the old x2 row. Minus 1 by 4 into x1 row is 1, 0, minus 1 by 3, 0, 4 by 3, 4. That we'll write here. And this will come out to be 1 by 4 minus 1 by 4 is 0. 1 minus 0 is 1. 1 by 4 plus 1 by 12 is 1 by 3. Here it is 0, minus 1 by 3 and 5. So this is our new x2 row. Let us write this in the modified table. So it is 0, 1, 1 by 3, 0, minus 1 by 3, 5. In a similar fashion we will write the S2 row also, new S2 row. New S2 row is equal to old S2 row minus its pivot column coefficient into the new pivot row, which is x1 row. What is its pivot column coefficient? It is 11 by 4. So this is equal to old S2 row is 11 by 4, 0, minus 1 by 4, 1, 0, 15. So whenever you are writing the row, it should be from the first variable to the resource column. Don't omit the resource column. Unless you find the resource row, you cannot directly find the values of BV. If you are not including the B column, how can you say that x2 is equal to 6, s2 is equal to 15, s3 is equal to 3? So for us to read out the values of basic variable from the table, we have to include the B column also. This is the old S2 row. Minus 11 by 4 into x1 row is 1, 0, minus 1 by 3, 0, 4 by 3, 4. This is equal to 0, 0. This is 2 by 3. This is 1, minus 11 by 3, 4. So this is the new S2 row. Let us write this down here. 1 minus 11 by 3 and 4. Let us cross check whether we are getting the identity matrix here or not. x2 to x2 should be 1, x2 to s2 should be 0, x2 to x1 should be 0. Correct. s2 to s2 should be 1, s2 to x1 and x2 should be 0. Correct. x1 to x1 is 1, x1 to x2 should be 0 and x1 to s2 should also be 0. Yes. So there is no error in our calculations. We can now find the value Zj. 2, 5, 1, 0, 1. Here it is 5 5s, 25, 25 plus 0 into 4 is 0 plus 2 into 4. 25 plus 8 is 33. So from the compared to our previous table, here we are getting a better Z. Previously it was 30, now it is 33. Now let us see if at least this is the optimized answer, or if we can make our Z any better. For that we have to find the net evaluation row as Cj minus Zj. This is 0, 0, minus 1, 0, minus 1. So for a max type of problem, Cj minus Zj is all 0 or negative. So there is no scope of maximizing the Z any further. So the maximum value of Z can be 33 and not more than that. And maximum Z is 33 and the corresponding variable values are x1 should be 4, x2 should be 5 and s2 should be 4. These are the basic variables, and s1 and s3 are zeros. So this is the solution. Now in certain textbooks, they may use a net evaluation row as Zj minus Cj also. That time the condition for max type is to get all zeros or positives. So I suggest you follow any one convention. So Cj minus Zj is what I always recommend. Cj minus Zj for a max type of problem, if it is all zeros or negatives, then the optimum solution is obtained. In the other case, we have to keep on trying for a better Z value by modifying the rows with the given formulae, and until we get the best solution or until the optimality is attained. So to avoid any confusion, I am writing this out here. The optimality condition for a max type of problem, in case our index row is Cj minus Zj, should all be 0 or negative. If this is attained, then that is the optimal table. For a min type, it should be 0 or positive. Now for example, if you are taking, if you are considering Cj minus Zj for max type, then it should be 0 or negative. And if you are considering Zj minus Cj for a min type, it should be 0 or negative again. So in the similar fashion, if you are checking with Zj minus Cj here, it should be 0 or positive, and here it should be 0 or negative. So don't get indulged with so many types of different conventions. I follow only one. So whether it is a max type of problem or a min type of problem, always remember that take your net evaluation row as either this or this, any one. And I am recommending you this. Always use this only, and then you don't have to remember so many things. You don't have to always get entangled with the concept or the definitions. Cj minus Zj, if it is your index row, then for a max type it should be 0 or negative. All the Cj minus Zj should be 0 or negative for a max type of problem, or it should be all 0 or positive for a min type of problem. So you don't have to worry with all these many possibilities. Remember only one thing, and that will be sufficient. Another important point that I would like to tell you is, here in the current problem we have considered as an example a max type of problem. In case the question is a min type of problem, the question is say something like this. Now if you know only max type of problem and you do not know how to solve with the min, or if you think you will be even confused with these two conditions, then I suggest you convert your given z to a maximization problem. How? It is the simplest thing that you can do. Maximum z is nothing but minimum minus z. If I am saying that z is maximum when it is 100, so z is minimum when it is minus 100. As simple as that. So if the given case is this, multiply this with minus 1 all together, and that will become a maximized problem. Let maximize z. This is the question. Say for example, the question is minimize z is equal to 3x1 plus 5x2, and we do not know how to solve with the minimization algorithm. We have some confusion, say whether it is NER or whether it is a minimum row ratio, whatever it is. Now I am converting this into a max type of problem. Let us see how. Maximize z prime is equal to my minimum minus z, nothing but minus 3x1 minus 5x2. Now this is your max problem. Subject to conditions, they are not changing, they are not going to change. The constraints, they are as it is. Only our min z is converted into a max z by multiplying with the minus 1. Now in place of your Cj, you will get a minus 2 here, a minus 5 here. Nothing else is going to change, and everything else is same. The how you find the entering variable row, how you find the leaving variable row, everything is, it's all this, every rule that we have applied, every rule that we have known in the max type is applicable here. So without any confusion, you can simply remember just one thing, that index row is when Cj minus Zj is all 0 or negative. So and until that condition is attained, you can solve the problem, and you get the optimum answer. So now in case your maximum z dash has come out to be say minus 40, or sorry, it might be plus 40, you will get some z dash is equal to say some 40. Then the given question is z, not z dash. So z will be minus 40. This is the minimum z. This will be the answer, for example. That is how we can solve the problem. For your comfort, I'll try to solve a problem on minimized type or min type of problem, with converting it into a max type and without converting it to a max type. I'll try to solve it in both ways possible, and if in case I solve it and upload it, the link will be given in the description below.
Thanks for watching. If this video was of help to you, please like it and share it with your friends. And don't forget to subscribe to our channel.